It's the second one, isn't it? The Sablavuris. The down one.
Yes, it's the one. Okay. That's
Okay.
We're ready. So, probably just move. Yeah, just so otherwise you can't. Okay, right. Okay. Okay, so good morning, everyone. My name is Alan Witter, and I'm the training manager for a company called GPP Training, and I'll explain in just a moment. We're just a very small subpart to a company called GPT, who are the designers, the engineering design company behind membrane tanks for LNG. So I'm going to explain that to you in just a moment. This morning, this is what I propose to try and discuss with you this morning. But perhaps just before I do that, maybe I should just explain to you my background. So initially, I'm a mariner. I started work at sea, and I have a Class 1 master's license, so I sailed at sea. I didn't actually sail as captain, but I sailed as chief officer on different types of gas carriers. And I also I moved from working at sea to working for an organisation called Warsash Maritime Academy based in Southampton here in the UK. And I worked there for about 18 years, where I ran a liquid cargo handling simulator and delivered gas-related training courses for seafarers. Most of the training courses that we did in the simulator were LNG, so for both membrane and MoS type LNG. We went through all of the types of cargo operations. And for the last 18 months, I've been working as a training manager for GPT Training, which is a subsidiary company to GPT. I'll explain that in just a moment. Maybe I can get rid of that. You don't need to see that. Okay. So this is what I'm hoping to go through with you this morning. I'd like to just kind of explain to you who GPT are. I will go through that a little quickly because we started a little later than we were scheduled to, but I would like to just kind of explain to you who GPT are. You may or may not have heard of GPT, so I'll just spend a few minutes explaining who GPT are, what they do, and where they fit into the LNG structure. And then I'll explain to you something about membrane tanks in general. So we'll talk a little bit about the concept of membrane tanks, what membrane tanks actually have to achieve, the basic requirements in the regulations for membrane tanks. And by then you will have realized, if you didn't know already, that there are fundamentally two types of membrane tank at the moment. One is referred to as the Mark III, one is referred to as the LN96. And for each of those, I'll explain to you how they're put together, what the components are that make them up, and I'll also explain to you how they're actually constructed. So hopefully, at the end of that, you'll have a fairly good understanding of what membrane tanks are, two different types, and how they're put together. So as we go through, if you have any questions, then feel free to ask them, jump in. So, okay, so let me just explain to you, in case you're not aware of who GPT are. So GPT is an engineering and design company. They're kind of strange in the sense that they don't actually build anything. They're a design company, and they're the company that have designed and patented and licensed the design to the shipyards for all of the membrane type LNG carriers that are currently in service. So GPT have existed for just over 50 years. As of last year, they became a public limited company, and at the moment there are, I think, just over 300 LNG carriers using membrane type containment systems, and there are currently over 130 new buildings that are on order, which will also utilize membrane containment systems as well. So GPT as a company have, I would say now, about 400 employees. Most of them are based at their headquarters in France, just outside of Paris, about 40 minutes west of Paris. But they also have representatives at all of the shipyards that are building membrane-type LNG carriers as well. GPT, just very briefly to explain that GPT is the concatenation of two companies, actually. Historically, there were two French companies. One was called Technogaz, and they developed one of these membrane containment systems, the MARC system. They came out with their very first attempt at an LNG tank for a vessel in 1964 with the vessel called the Pythagore. And as you can see from the slide there, she was very small. It was actually a converted vessel, and the tank was very tiny, only 630 cubic meters. So that was the very first type of membrane tank. And the second company, another French company as well, was called Gas Transport, and their technology was called the NO system, and they came out with their first vessel in 1969. And the two companies kind of joined together in the mid-90s. So instead of competing with each other, they joined forces, and so the two separate companies became known as GTT, Gas Transport and Technigas. And today you will still hear of these two membrane technologies, the GTT NO96 and the MARC containment system, usually referred to as the Mark III. So that's just a little bit of background to sort of set the scene there. So I mentioned to you that I work for a company called GTT Training. It's very small, actually. The main company is GTT, and as I said, there's about 400 employees. GTT Training, very small, only 4 employees. There's a general manager, myself, and 2 software engineers. And there are also 2 other small subdivisions for GTT. One is GTT North America, so they have an office based in America with about maybe half a dozen people working there, because they foresee an emerging LNG market in the US. And we also have a small subsidiary company called Cryovision, and they specialize in the production, development, and the selling of systems that will assist with the maintenance, primarily with the maintenance and inspection of membrane systems on vessels that are currently in service. So that's kind of GTT as an overview. So I mentioned to you that GTT don't actually build anything, which is kind of strange for a very successful company. So this slide is just to briefly explain to you what GTT actually do. So at the beginning, when a shipping company decides that they want to try to order an LNG carrier or some kind of LNG facility, they will often discuss with GTT at the pre-design stage what their aspirations are, and they'll talk to GTT, and GTT will help them to decide whether or not their aspirations and goals will be achievable. When the company's decided that they want to go ahead and build something, they will have put out a tender to the shipyards, and they will have agreed a contract with the shipyard. And once that's been done, we enter into the detailed design stage. And at that stage, GTT will produce all the plans and drawings for the membrane containment system and the cargo handling system for that vessel, and those plans will be provided to the shipyard. And then the shipyards will go ahead and build the vessel in accordance with those plans. During the construction of the vessel, GTT have every one of the shipyards that are licensed to build these type of tanks. They have representatives there. They have a team of people, offer advice and assistance, and to help with the inspection at various stages through the construction. They're there during the construction. And once the vessel comes into service, shipyards will typically guarantee a vessel for an LNG vessel, typically for about 2 years. And then after that, it's kind of the shipyard are not really interested because it's out of warranty. But GTT offer assistance throughout the lifetime of the vessel, and they'll offer assistance to the company that owns and operates the vessel as required. And there are also periods during which the vessel has to be maintained. So there are shipyards which are licensed to maintain and repair these membrane tanks. And once again, GTT has a relationship with them where they will provide technical assistance to those yards and to the companies during the maintenance periods of the vessel's life. So that's where GTT kind of fit in. That's what they do. They don't actually physically build or construct anything. So this is really just kind of summarizing what I've just said. As far as the shipyards are concerned, they pay a license fee to GTT, and for that GTT will provide them all the detailed information they need to build those tanks and all the technology. As I mentioned, GTT have a presence in the yard. GTT also work with other organizations in research projects as well. They do a lot of work with classification societies and universities as well, for specialist areas such as liquid motion and sloshing. They've done a lot of work in those areas. Different types of material research, materials that are used in the insulation systems and the membranes, all kinds of joint research projects they're involved in as well. So as far as the ship owners are concerned, the companies that actually own the vessels, GTT offer technical service advice to them, and they have commercial arrangements which they refer to as technical service agreements, so that companies have the opportunity to pay a fee, and then they can call on GTT 24/7, 365. If they have any problems at all, then they have the technical assistance throughout the life of the vessel. And I mentioned briefly as well just now that the repair shipyards, they have to be licensed as well. And once again, GTT will provide training and technical assistance to those shipyards so that the shipyards can go ahead and maintain the vessels that use these types of tanks. So again, I apologise, I'm not really sure of your backgrounds and how much you know, so I thought I would just put a couple of images up here to show you the sort of examples of where membrane containment tanks are used. So the most widely known type of use of membrane tanks are large-scale LNG carriers. So that's the one that most people would be aware of. More recently, in the last, let's say in the last decade, we've seen the evolution of something called floating storage and regasification vessels, which allow countries to have a sort of a fast way of importing gas by, instead of building a conventional import terminal, we take a standard LNG vessel, convert it to be a regasification and storage unit, park it alongside a jetty or maybe in an offshore installation, and we bring conventional LNG carriers alongside where they will discharge into this vessel, and this vessel will turn the liquid into a vapor and distribute it directly into that country's gas network. So membrane tanks are used for those types of vessels as well. In the very near future, under construction now, there are 3 floating production, storage and offloading units for LNG. Now, for years, there's been FPSOs for oil, and we're just on the cusp of getting the first LNG FPSOs. They're generally referred to as FLNG. So here, you have an installation that is located offshore somewhere where it's commercially not viable to lay a pipeline all the way back to the shore. So when they take the gas out of the ground, normally we would send the gas back through a pipeline to the shore where it's processed. But there are certain locations where it's not viable to do that. So the idea is that these units will be taken to those locations, and they have risers coming up from the seabed, take the raw gas out of the wells, and they have all of the production equipment that you would conventionally find ashore is all located on the top sides here. So we can clean up the gas, separate out the heavier hydrocarbons from there, and we can separate out condensates, LPGs, store them in the tanks, and LNG, and conventional product carriers, LPG carriers and LNG carriers will come alongside and offtake from here rather than going to a terminal. So this is the largest of the 3 that's being built, and you may have heard of this. It's called the Prelude. If you haven't, maybe Google it, because it's a really amazing project when she's finished. I've stood next to the hull in the shipyard in Korea, and it's just vast. It will be the largest man-made floating structure in the world when it's completed. And you can see the capacity there of the LNG tanks, LPG and condensate. You can see she's going to be 600,000 tons when she's fully ballasted and 488 meters long. It's vast, huge. And they're going to use membrane containment systems in there as well. The GTT containment systems are also used in land storage tanks as well. So you may come across GTT's name in relation to shoreside storage tanks. There are other technologies that are used there, but GTT have quite a few storage tanks ashore. And perhaps most relevant maybe to this course, to this project that you're involved with, the use of membrane tanks for LNG bunker vessels. Now at the moment, you're probably aware that the small number of LNG fueled vessels that exist in the world at the moment all use Type C tanks. And that's primarily because they're all very small and they're on very short sea passages. They're either ferries or they're platform support vessels, that kind of thing, that are in and out of port on a virtually daily basis, so they can refill those small tanks on a regular basis, and their capacity requirements are quite small. As far as bunker vessels are concerned, you're going to need something a little bit bigger. And once you start to scale the size of tanks up, there comes a point when, although you can physically use Type C tanks, they're very heavy, they take a lot of space, they're not very space efficient, and there comes a point when the use of membrane tanks becomes much more attractive. At the moment, there's a bunker barge here that's being constructed or is going to be constructed for the company called Argos, the bunkering company in Rotterdam. This one was originally designed with Type C tanks, but they changed the design when they looked at the amount of LNG they could carry. It was about a 55% increase by switching. And in February of this year, it was publicly announced a barge, an LNG bunker barge, to be built in the US. It will be the first one to be built in the US, and we hope there'll be many more. But this will also use a membrane containment tank as well. Okay. So hopefully that gives you a little bit of an idea. Oh, sorry, last slide here on this little introduction is the actual fuel tanks on vessels as well. So as I mentioned just now, all the existing vessels, quite small, they're all using Type C tanks, but these are some of the GTP designs for membrane tanks that could be used on larger vessels. So this Ropax ferry here was actually a design that was almost built. This was for Brittany Ferries, and this was called the Pegasus project. And they were going to build a new vessel, and they were going to use a membrane tank. And this was where it was going to be located. One of the nice advantages of a membrane tank is that you can kind of fit it into any sort of space that's available, so it's kind of neat to fit in. But anyway, they were going to build with that. The project fell through in the end, so it didn't actually come to fruition. But these are just some other, the diagrams here show you some other examples of sort of GTP's concepts for where tanks can be fitted in. There's one here for a container vessel, here for a bulk carrier or something. But, you know, they can be fitted in pretty much anywhere. So in the future, as vessel sizes become bigger, when you need bigger fuel capacities for vessels that are going to be on longer routes, you're going to need greater quantity of LNG fuel. You probably know already that the energy density of LNG is much less than conventional fuel. So you're going to need bigger fuel tanks for the same amount of energy. So when you need bigger tanks, you're going to see that vessels in the future will start to use membrane tanks rather than the Type C tanks, because they're lighter and you can fit them in more easily into different locations. Okay, so that's my kind of little introduction to GPC and where they fit into the LNG industry. Any questions on that so far?
Actually, how do you approach to solve the sloshing problem between membrane tanks?
Let me come to that. I'm going to address sloshing in the next session, so we'll look at that in a moment. And please go ahead, and if I don't answer your question, go ahead and ask it again then. Yeah, Leonardo.
Only about the location.
Yep.
It's an issue that we have been asked a lot of times until now, and it's also our question. If it is, for example, more sufficient to put the location of the tanks to have it at the middle of the vessel or at the back, like Virgin Grace, which is better and for safety reasons and for efficiency reasons, in your opinion? Because currently I'm saying that you are using the middle of the vessel in order to install.
In this design here, which was for the Pegasus ferry, I think you can probably sort of make out that the engine room is quite close to this. So one thing is, it's going to be convenient to have it located reasonably close to the consumers. So that's kind of, it's not essential.
We need less pipeline system.
Yeah, and of course the pipeline system that goes from the tank, or from your gas processing, when you're going to turn it into a vapor at whatever pressure that the consumer requires, that piping has to be protected in some way. So usually it's in a trunking, and there are restrictions about where that piping can run. So having it located reasonably close to the consumer is an advantage. It's not insurmountable. There's ways around that, but that's a kind of like an obvious choice, I guess, to begin with. But in terms of where it can be located, there's lots of different options. I don't have the example here, but another GTP conceptual design is what they refer to as an exoskeleton tank. You maybe came across that in some of the conferences that you saw. I'm sure Mr. Barrett would have shown that. But the idea of an exoskeleton tank is simply you take a membrane tank and you build a kind of a shell around it, and you can pick it up and you can locate that on the deck if you want, in the same way that you see like the Viking Grace has Type C tanks down on the arse end out in the open. So you could do that with a membrane tank as well. There's lots of different possibilities and options. But the examples here are trying to show that you can try and utilize space within the vessel wherever it might be available. Because the fundamental point about any commercial vessel is it makes money on transporting goods or people. And as I touched on just now, that it's recognised that for the same energy content as a given heavy fuel or diesel oil tank, you're going to need a bigger, about 1.8 times the volume of LNG to give you the same amount of energy. So, you're going to sacrifice some of your cargo carrying capacity if you switch to LNG. So one of the advantages of the membrane tank is it can be made virtually any shape you like, and it can be fitted in sort of locations where you're going to minimize your loss of space. So there's advantages. But anyway, so
it also depends on the vessel.
Yeah, it depends on the vessel as well. Depends on if you're a container ship or a passenger vessel, because of course one of the issues that people are talking about a lot at conferences at the moment is what they refer to as simultaneous operations. So if you're going to be bunkering your passenger vessel or your ro-ro vessel or whatever it is, are you going to be allowed to carry on with other operations like loading and discharging of people or cargo at the same time? Because it depends partly where the tank is located. There's all kinds of hazard studies that have to be undertaken before you can go ahead and do that to make sure that it would be safe. So the location of the tank is quite important, actually, not just from an engineering structural point of view, but from an operating the vessel point of view as well, because it may impact on whether or not the vessel can conduct simultaneous operations. And if it can't conduct simultaneous operations, if you can't load your cargo or your passengers at the same time as you're filling these tanks, you're going to extend your port time, which costs money and reduces income. So it's kind of all connected together. So it's quite a fundamental thing about where you locate the tank.
How much do you pay for?
Type C tanks? Well, the advantage here is that you can make it any shape you like, and you can fit it into a sort of a box-shaped sort of space here. If you think about a Type C tank, if we wanted to take this room as an example, okay, we could construct a membrane tank in here which would completely fill this room. But if we wanted to put a Type C tank in here, so we've got a certain height, we can have a certain diameter of the tank and a certain length, but there's a lot of wasted space around the outside of that tank that you can't do anything with. And the IGF code requires certain requirements about that space.
What percentage is already?
To give you an example, I don't think you can just say, oh, if we took this room, what's the percentage difference? I don't think it's quite as simple as that. But to give you an example, this bunker vessel that I mentioned to you, when the company Argos originally contracted this vessel to be built, she was going to have a series of Type C tanks inside. So the physical size of the hull didn't change, exactly the same. So this room is a good comparison. So when they calculated, I can't remember the numbers off the top of my head, but they calculated how many cubic meters of LNG she could carry in a Type C tank. Then they considered what would be the capacity if we had a membrane design. And it was, I think I'm correct in saying, 55% greater volume of LNG she could carry by changing to a membrane tank design with exactly the same hull dimensions. So if we took just a round number and said 50% greater, but it's not only about the capacity, it's also about the weight of the vessel as well, because the Type C tank is very heavy, depending on the pressure you want to operate at, and the membrane is very light in comparison. So not only do you get a greater capacity, the dead weight of the vessel is less, so you need less energy to propel it, and also the draft of the vessel is less as well, which is important in harbour and port areas and inland waterways as well. So there are certain advantages to the membrane system. Okay? So yeah, to answer your question in a very rough, unscientific way, but I would say about 50% based on the experience of that particular vessel. Okay, so now if I can just change presentations, because perhaps not very cleverly, I need to just go back here. Okay. And hopefully that'll work. Okay. So in this session here, I want to give you a sort of a general introduction to membrane tanks, to the philosophy behind a membrane tank, without looking at a particular design. Did I?
No, only that we are sharing this one.
Okay, so I've got sort of three parts to this little presentation. So the first part here is just to give you an oversight into the sort of philosophy behind the membrane tank, and then we'll have a look at something about the sort of some of the design characteristics that are common to membrane tanks, and then lastly to address the question that you mentioned about liquid motion and sloshing in particular. So okay, regulations for these tanks. Now, at the moment, all of the tanks are built under the IGC code. So all LNG carriers have to comply with the IGC code, and the bunker vessels as well also have to comply with the IGC code. When we look at tanks for fuel on vessels, they will be built under the IGF code. But the draft IGF code, as it stands today, as far as the tanks are concerned, the words are almost identical to what you find in the IGC code. So you know, that's going to be okay. So okay, this is the IGC code, and if you didn't know already, or maybe you've never heard of the IGC code, but it actually derives its authority through SOLAS, through Chapter 7 of SOLAS, carriage of dangerous goods. So any vessel that's going to carry 5 bulk has. Fine. So what does it say about tanks? So for tanks for LNG, in the IGC code, you can have independent tanks or you can have membrane tanks. If you read the IGC code, there are actually 5 categories of tanks. But as far as our relevance for LNG is concerned, we have 2, independent and membrane. So if we look at the independent type, the independent categories are broken down into type A, B, and C. So type C are the ones that we've mentioned already and you are perhaps familiar with, that you see on currently LNG fueled vessels, the cylindrical type tanks. And these types of tanks will have pressures greater than 2 bar typically. The IGF code limits them up to about 10 bar. So they're pressurized tanks. Type A and B currently are not actually built for LNG, but there are projects and plans out there. There's a company called LNG ABOT, I think it is, who have proposed a plan for a Type A tank for LNG. Type B tanks are if you're familiar with LNG carriers, the ones with the round or spherical tanks, sometimes called MoS tanks, so they would fall under that category. But the membrane tanks under the IGC code we see here, their maximum design pressure is limited to 700 millibars, 0.7 of a bar, and at the moment, the only company that has ever designed membrane tanks is GPT, and we have these 2 technologies, 2 types of membrane tank referred to as Mark III and the NO96. Again, you may know that in Korea this year, there's been 1 vessel order for a membrane tank with a brand new Korean-based design. So that'll be interesting to see how that comes out. But at the moment, as it stands, all membrane tanks are only those that are designed by Mark III. So we're going to look into these more detail as we go through the morning. But this is the Mark III technology. This is what the tank looks like from the inside, at least on a full-size LNG carrier. And this is the NO96. And I'll explain, how they're put together, what they're composed of a little bit later on. So I said this session was a little bit about understanding the basic philosophy behind any type of membrane tank, doesn't matter whose design it is. And essentially, the most fundamental way to think about a membrane tank is it's just a lining inside the hull. So if you look on the diagram here, we have the outer hull. There's a kind of a label missing here, but that should really identify this as the inner hull. So this will be a ballast tank in between here. And then really, the membrane containment system is just a lining on the inside of that inner hull. And the function of that membrane system or that lining is simply to contain the cargo within that space, protect the inner hull from low temperatures and to transfer the loads onto the inner hull. The membrane has little structural strength. So taking that a step further, this is a little bit out of the IGC code here, but I think it explains the philosophy behind the membrane tanks very neatly. So if you can excuse me just to read that out, and then I'll just go through the bullet points below it. But this is what the IGC code says. Membrane tanks are non-self-supporting tanks, which consist of a thin layer, the membrane itself, supported through the insulation rather, by the adjacent hull structure, by the inner hull. Okay. The membrane has to be designed in such a way that the thermal expansion and contraction and other stresses on the hull are not going to damage that membrane in any way. So that's an important consideration. So we can kind of summarize that by saying, first of all, as hopefully you saw in the last slide, that the membrane and the hull are intimately connected together. What happens to the hull happens to the membrane. What happens to the membrane is transferred through onto the hull. So that's a very important consideration, which I'll come back to in the next few minutes. The containment system simply transfers the load, the weight of that liquid, and the dynamic forces, the movement of that liquid. The containment system or the insulation has to transfer that onto the inner hull. So that insulation system has to be strong enough to be able to transfer those loads through onto the inner hull. It's no good if it becomes crushed and flattened by the weight of the liquid moving around inside the tank. So that's really important. So the membrane's got to be thin, and obviously it's got to be suitable for cryogenic temperatures, minus 160, so that's pretty obvious. But this is important as well. The membrane has to be flexible enough to absorb hull deformation as well. So the hull is going to flex when the vessel's at sea. We've got bending moments, we've got statical bending moments, dynamic bending moments, we've got local bending. So we'll look at some of that stuff in a minute. But that's the philosophy behind the membrane. That's what it's got to achieve. This diagram here shows you kind of a cut-through of a conventional full-size LNG carrier. The concept will be exactly the same. The shape may be different, but the concept will be the same, whether it's a fuel tank for a ferry or whether it's a full-size LNG carrier. The shape is adjustable. But here you can see in this diagram we have the membrane, we have some dark green, that's the primary insulation here, then there's a secondary membrane here, a secondary barrier, and then some lighter green, the secondary insulation, and then directly onto the inner hull, the ballast tank. So that's the kind of main concept behind the membrane. I mentioned to you very briefly in the slide where I showed you the different types of tanks, the maximum pressure. So this is again a little quote from the IGC code, and here it's saying that the design pressure normally shouldn't exceed 1/4 bar, 250 millibars, but you can, if the inner hull scantlings are strong enough to be able to take it, membrane tanks can go up to 0.7. Now, I can tell you right now that all of the conventional LNG carriers that are in existence today operate with a tank pressure of 1/4 bar, 0.25. I mentioned to you floating storage and regasification vessels earlier on, FSRVs. Some of the newer ones of those operate at 0.7 bar. But there's a kind of little restriction they have. When they're alongside, or when they're operating in regasification mode, they operate at 0.7 bar. So they're utilising the maximum allowable pressure because there are operational advantages to that. But if they were to switch back to being a conventional LNG vessel, or if they were to sail at sea, they would switch back to 1/4 bar. It is assumed, and it's being designed for the bunker barge vessels, that they will operate at 0.7 bar. So again, there's operational advantages to having a higher pressure. That's the basic limits for membrane LNG tanks. Now again, another little bit from the IGC code, we kind of touched on this just now. This is saying that the tanks, the membranes, have to be able to withstand all kinds of loads. And all these bullet points here are taken straight out of the IGC code, but when you design one of these tanks, these are the considerations that you have to be able to satisfy that the membrane containment system will be able to withstand all of these forces. So the obvious ones are the internal pressure, the weight of the liquid and the vapor pressure inside that tank. Then you've got external pressures, the weight of the ballast. When your cargo tank is empty and your ballast tanks are full, there's a substantial amount of ballast pressure on that inner hull structure, so it has to be able to withstand those. The dynamic motions of the vessel as well. So when the vessel's at sea, she's moving around, there's liquid movement inside that tank, and we also have to think about hogging and sagging. When you cool that tank down, you're going to cool it down from potentially plus 40 to minus 160, a 200-degree change in the thermal contraction of that structure has to be acceptable as well. So sloshing loads, the question that you raised just now, we have to consider those as well, so that's very important. Chip deflections, bending moments, the weight of the cargo tank and the supporting insulation structure, and any other structures that you find inside the tank. I'll point some of those out to you later on. So there's quite a lot of things that you've got to consider if you're going to take on the idea of designing one of these things. These are all the things that these membrane tanks have to be able to withstand. So a couple of slides just to highlight here some of the forces on the hull. So this one I guess most people would be familiar with. The most obvious ones in the longitudinal sense, we have hogging and sagging. These of course can be created by the way the vessel's loaded, or when the vessel's at sea, by the bending moments and movement of the water around the hull can create those as well. So there's always going to be longitudinal hogging and sagging deflections as well. Transversely, there are little, but not very much. Transversely is very easy to manage. The forces are much smaller, so they're not really too big an issue transversely. This one is quite an important one. In fact, it's a very important one. Maybe isn't quite so obvious. I mentioned ballast water pressure just now. So if you imagine the cargo tank is empty, but the ballast tanks are full, think about the inner hull structure on the bottom. You can see here would be our inner hull. Here are the stiffeners underneath there. But that ballast water pressure creates local deformation in between those stiffeners. So you get small amounts of movement of that inner hull. It's about 4 or 5 millimeters of movement in there. And so our membrane, which is attached, remember it's intimately attached to that inner hull, has to be designed to be able to absorb or withstand all of those local pressures, not just the global sort of hogging and sagging longitudinal pressure. So that's quite an important one as well. I mentioned in the cutaway diagram, I showed you the primary membrane, the primary insulation, and I said, oh, there's a secondary membrane as well. This is another requirement for all membrane containment systems, another requirement from the IGC code. And this table, taken from the code, I've highlighted the bit that's relevant here, the membrane part. It says that we have to have a secondary barrier for the complete secondary barrier for any membrane tank. So the idea being that because our membrane is so thin, if the primary membrane should fail in any way, if it should leak, we have to have a secondary membrane so that we're ultimately going to protect the inner hull from low temperature. So all membrane tanks, doesn't matter who's designed them, always have this feature of a primary and a secondary membrane to contain the liquid in case of a failure of the primary membrane. The secondary barrier, the requirement in the IGC code, I've highlighted it up here. The main requirement is that it must be able to contain any leakage from the primary barrier for at least 15 days. So the people operating the vessel have got 15 days to be able to work out what the hell it is that they're going to do with this cargo. And in most cases, certainly in DPD's design, there's no reason why you couldn't sail around with the liquid at the secondary membrane almost indefinitely, but the requirement is it must be able to hold it there, and the design must demonstrate that it can hold it there for at least 15 days, so you've got time to take some other action to get that cargo out of the tank, with the ultimate aim of being able to protect the inner hull from low temperature. Okay. One final feature that you'll find on LNG carriers, and it may or may not be relevant to the tanks that are used on vessels when LNG is used as a fuel, but certainly the LNG carriers, A design feature that's common to all of them is that they have a cofferdam space between each of the cargo tanks. Now, in a conventional vessel, your hull is split with major transverse bulkheads, but there'd only be one. The problem here with a membrane-type vessel is if you only had a single transverse bulkhead and you had the insulation system on both sides of that, then eventually the cold is going to get through the insulation because no insulation is perfect, and temperature, certainly in the middle of that transverse bulkhead, could get potentially quite low. Now, all steel has a minimum temperature which is designed to work at, and if you go below that, there's a risk that the steel will become brittle. So to resolve that problem, LNG carriers have a double transverse bulkhead with the cofferdam space in between, and there is a heating system in there which is designed to maintain the steelwork of those cofferdams above a certain temperature, above 5 degrees. Okay. So yeah.
So I expect that due to the low temperatures, the steel used for the membrane tank itself would probably be cryogenic steel, but the outside steel of the inner hull is high tensile steel or something like that.
Okay, good question. So I'll explain the materials, exactly the materials that are used for the membrane. Obviously, they have to cope with minus 160 because that's what they're going to be exposed to. The inner hull itself, and again, I think I have a diagram, we'll probably come to it in a minute, but let me just answer your question. Inner hull itself has to be designed with steel that goes down to a certain temperature. Now, how do we work out what that temperature is going to be? So again, in the IGC code, it sets criteria, like the ultimate disaster criteria. So what it says in the IGC code is your disaster situation is your tank is full of cargo, full of LNG, and your primary membrane is completely fouled, and the liquid is now at the secondary membrane. So that's your first stage of the disaster. The second stage is it defines the outside environmental conditions, so the air temperature, the wind speed, and the seawater temperature. So in the IGC code, it says that the air temperature is 0, the wind speed is 0, and the seawater temperature is 0. I might be wrong about that, actually. I have a slide with those numbers on. There's a slightly tougher requirement under the US Coast Guard regulations, actually, which is what all the ships are built to. But given those criteria, the designer, GTT in this case, makes a thermal analysis of the structure given those criteria. So here we're primarily looking at the heat transfer, the insulation properties. So they will do a detailed thermal study of that structure, and given those criteria, they will tell you what the minimum temperature that the steel will go down to around the hull. So it's actually colder at the top because as you go below the seawater, below the waterline, seawater keeps it warmer. Having defined those temperatures, the shipyard will then select a grade of steel which is appropriate for those temperatures. So the steels are usually graded A to E, and each one goes down to a slightly lower temperature. So in the construction of the vessel, it will be defined which part of that inner hull will have which type, which grade of steel. And for the people who operate the vessel, the IGC code requires that they have a diagram, they have information on board that tells them what those minimum temperatures are, so that if this disaster situation ever occurred, and maybe if it got worse, let's say the secondary barrier was leaking as well, they know what the minimum temperature the inner hull can take. They can go measure the inner temperature, then go into a ballast tank and measure it. And if it's going below its designed temperature, then they have to take some action to be able to protect that inner hull. Because if you didn't, ultimately, if the inner hull became embrittled, it would just fracture and eventually the hull would break up. So that's, I hope that answers your question. But there's a very important criteria in the regulations and in the design to address exactly that question. What grade of steel do we use around the inner hull? I'm certain I have a slide that will pop up in a minute and you'll see that. Yeah.
Question one of our students regarding the material and environmental friendly, how much space does a membrane occupy? We will cover this.
I'm going to give you a lot of detail on exactly the materials and the dimensions of those materials Environmentally friendliness? I'm not too sure. Let's see. I hadn't really thought of it in that way. I think it's pretty environmentally friendly. But I'll address that when we actually look specifically at the membrane construction, if that's okay. Because I've got lots of diagrams that will help to address that. So, in the second part of this little presentation here, some ship design requirements. Now, these are, actually there's the thermal analysis bit we were just talking about there. The first things I'm going to show you some basic sort of design principles, but these are applicable really to the full-size LNG carriers. One of the things I want to make clear to you is that the membrane tanks can be designed in any shape. I mean, I kind of tried to mention that when I was showing you the sort of shapes of tanks for vessels that will use them as fuel tanks. They can be any shape. Anyone who's been involved in LNG carriers has this kind of, when you say a membrane tank, they have this kind of prismatic shape. You know, that's the sort of standard LNG carrier shape. And that is a kind of optimized, the best shape you can come up with for a full-size LNG carrier. But just be clear, you can have any shape you like. So, in terms of conventional LNG carriers and the size and number of tanks, GTT's current recommendation is for vessels less than 180,000 cubic meters, you have 4 tanks. It says 3 plus 1, meaning that potentially these 3 are the same size, and the forward tank is a slightly different size and shape, of course, because of the finer lines forward end of the vessel. For vessels greater than 200,000 cubes, then they suggest a 5-tank configuration. Anything in between those two, then you need to look at a little more detail about how you want to use that vessel, and they'll come up with the best tank configurations. Now, I mentioned this prismatic shape, so let me just emphasize again, this is kind of optimized shape for a conventional LNG carrier, but we can build for fuel tanks, they can be box-shaped, rectangular, any shape you like. Part of the reason for making them this shape for the large LNG carriers is related to sloshing as well. Part of the reason for these large chamfers here, at the top and the bottom, are to reduce the sloshing forces in the tank. It's also useful to have a fairly standard design shape, because when you go to build these things, it's all well and good coming up with a design, but to make a product, to industrialize it, to make it commercially viable, you have to make it out of as many elements that are identical as possible, so you can mass produce those elements to keep the cost down. So there are lots of reasons why it's kind of ended up this way. But that's conventional shape for conventional LNG carriers. Now, touching on sloshing, it has been identified that the liquid motion in the tank can be a problem to conventional large-scale LNG carriers. And one of the things that we can do here is to reinforce both the insulation system and the membrane in certain ways, and I'll show you some of the ways we can reinforce them later on. But whereabouts do we reinforce them? Well, really it depends on how you want to use your vessel. If you have a conventional LNG vessel that's going to be sailing the oceans, loading and discharging cargoes in ports, then we can say that we need a certain type of strength requirement, because we can predict what type of sea environments and motions that the vessel will encounter. If we're going to have vessels that are going to work in an offshore environment, like this regasification vessel here, which is discharging on an offshore submerged buoy, which there are a couple of these located off of the coast of the US, or if we have these FLNG projects, these vessels are going to operate out in open waters. They're not going to be sailing, but they're going to be moored in open water, and they will at some point have cargo tanks that are half full, and the vessel is going to be subject to some motion. So lots of studies are being done by GPT to analyse the liquid motions in the tank. As a result of that, each different vessel that's built, there will be a requirement for reinforcing the membrane system in different areas within the tank. So we don't reinforce the whole lot, because if you did that, it would cost more and it would potentially weigh more as well. So we only reinforce where it's felt that it's necessary. It's a bit of a strange diagram, first of all. If I can just explain what you're looking at, this is a kind of fold-out membrane tank, if that makes sense. So here's, like, imagine that's the forward bulkhead. These are the port and starboard sides. Here's the bottom of the tank, the top of the tank, the upper and lower chamfers, and that will be the aft bulkhead. We've kind of just unfolded it all. And what this is showing is on the bottom of the tank and in these areas here, we would have the dark blue, which would be standard membrane. And then we can have, in the yellow areas, we've identified that we need some reinforcement here, so we can reinforce the membrane. And in the light blue areas, we've identified that in these regions, we need even more reinforcement. So we've got a different type of reinforcement, slightly stronger level of reinforcement. So we have options in the design to be able to strengthen the membrane in specific areas to enable that vessel to be utilized in certain different trades or environments, depending on what the vessel's been designed for. Okay, so boil-off. Boil-off refers to the natural evaporation of the liquid in the tank. No insulation is perfect, so whenever you put liquid into a tank at minus 160, there is always going to be a certain amount of heat leaking through. Up until about maybe 10 or 11 years ago, the membrane tanks and the MoS tanks as well, actually, their standard boil-off, guaranteed boil-off rate was 0.15% of the liquid capacity per day. So every day you could expect about to lose a max, or no more than 0.15% of the liquid volume. Now at the time, all of the LNG vessels were powered by by boilers, by steam propulsion. Boilers, steam propulsion, consumes a huge amount of energy, so you need a lot of fuel, so such a high boil-off rate was not a problem. Now in the last decade, we've seen the emergence of LNG fueled engines, natural gas fueled engines, and those engines are either medium speed diesels or slow speed diesels, and they are much more efficient, so they're going to consume less fuel. So not the only, but one of the big drivers behind trying to reduce the boil-off rate for these membrane containment systems is the fact that we now have engines that require less fuel. So we don't want to waste, we don't have so much boil-off that we burn some and then we've got a load left over that we've got nothing left to do with, we're going to waste it. So one of the things that changed over the last decade is there's been a lot of desire from the operators and owners to get the membrane systems changed so that their boil-off rates are much lower now. And again, I'll show you through the morning some of the design changes that have happened to be able to do that. So this is the diagram I had in my mind when you asked me the question about the inner hull just now. So I mentioned that one of the key principles of the requirement for any membrane system is it protects the inner hull from low temperature. And what I was trying to explain to you is this thermal analysis that's done. So here at the top are the criteria, the environmental criteria requirements set out by the IGC code. So I knew I had that slightly wrong. The air temperature was 5 degrees, so I think that's 0. Seawater temperature is 0, and no wind speed. Now, strangely, I hope I'm not going to offend anyone who's listening that's from the US now, but every country in the world, bar one, accepts the IGC code and the requirements in the IGC code. The US, a little bit different to everyone else. They've got their own set of rules which are contained in the US Code of Federal Regulations, and they're by and large, virtually word for word, the same as the IGC code, but there are some differences. And this is one example where they're a bit different. So in their criteria here, they're a little tougher. They say that, remember the liquid is at the secondary membrane, and they say that the air temperature is minus 18, the wind speed is 5 knots, so you have a wind chill effect now, and the seawater temperature is still 0. And so given those criteria, that's the criteria that we would then do our thermal analysis and calculate what the temperature would actually be on the inner hull, and from that we then select the appropriate grade of steel. So there's different grades of steel that are used around there. I have another diagram, but not in this presentation, that shows those different grades of steel. Last little bit here is I showed you a diagram earlier and identified the fact that we have 2 transverse bulkheads between each of the tanks, so that what I refer to as a cofferdam between them. I said there's a heating system that goes in there, and it's not a very exciting diagram, but this is the heating system that's contained within that cofferdam. And it's essentially just a series of pipes. There's a certain length of pipe, you get a certain amount of heat transfer through them, and we have a system that circulates a warmed water glycol mixture around that system, and it's regulated automatically how much flows through it. But the object is that it maintains the steel of the cofferdam bulkheads always above 5 degrees centigrade. We don't want it to get too hot, because if you put heat in, that's going to end up in the cargo. We don't want it to be more than that. But we want to make sure that the steelwork that's used in that bulkhead doesn't ever get too cold, so that there's a risk of it becoming brittle. And actually, in the IGC code, it considers this to be an essential system, and it requires full redundancy of this system. So it's a bit hard to make out at a glance, but actually there's a total 100% duplication of all the pipe work in here. So there's 2 sets of coils, there's 2 sets of pumps, there's 2 sets of everything associated with this system, because there is this kind of potential risk that if one system failed and you didn't have any heating going in there, and potentially you could get a drop in. It's not very likely to happen, but you know, because it's a potential problem, that's the rules are designed to make it. Okay. So that's the cofferdam heating system. Now, the third little part of this presentation addresses a question you were asking earlier about liquid motion. So this is really quite a big thing, particularly for the full-size LNG carriers. Now, this is much less of an issue. In fact, it's virtually a non-existent issue for LNG fuel tanks, because they're so much smaller. It's basically, from the studies that GTT have done so far, from small-size tanks, forget it. It's not even going to be an issue. But certainly for large, full-scale LNG carriers, it's always been an issue. So sloshing is about the motion of the liquid, and the video bit works here. Yeah, okay. So these are test tanks that GTT have in their laboratories, and these couple of little video clips here are just showing you the different types of liquid motion you get, whether the tank is almost full or almost empty. So that first one, at high levels, is referred to as a standing wave, and at lower levels you can get a slightly worse situation where we can have what's called a progressive wave moving across, and there's quite a potential for quite a high impact force on the sides of the tank. So you know, this is potentially a big problem with liquid motion in these tanks. Now you might actually ask, well, in any other type of vessel, if you think about any other bulk liquid vessel, an LPG ship, an oil tanker, a chemical tanker, first thing they do is they put a bulkhead in the centre line, and that either eliminates or certainly massively reduces the liquid motion problem. So why don't they do that here? Well, there's 2 reasons for that. One is because you physically cannot construct a centerline bulkhead on a membrane which is in itself essentially about 1 millimetre thick. There isn't the structural strength to be able to do that. So whilst we could have 2 tanks side by side, we'd waste a lot of volume and space in between them. But the reason why we persevered with having this huge tank without any centerline division is because from a thermoanalysis point of view, the larger the volume you have of cold liquid compared to the surface area of the tank, then the lower the heat influx in through that insulation. So by having a bigger tank with a relatively small surface area, you automatically reduce the heat going in and therefore the boil off. If you made lots of small versions of these tanks, that ratio would be greatly changed and your heat inflow would become much greater. So in terms of insulation performance, it's better to have a big tank like this with a smaller surface area. Anyway, it's not just about liquid sloshing and slamming into the side of the tank. There's also this structure in the aft end of all membrane tanks referred to as the pump tower that contains the loading pipe and the discharge pumps and the level gauging systems and all the other bits and pieces all fitted on there. So if you imagine the liquid swirling around inside that tank, there's a lot of force on that structure. So we need to analyse that and determine what those forces are going to be in order to make that structure strong enough to be able to withstand those forces. So those are the 2 kind of elements to the 2 parts to sloshing. We have the impact of the waves and the drag forces on the tower, and both of those have to be determined in order that we can build a structure that's strong enough to withstand both of those. So there's a couple of I've got a few slides here, but this first one is just going to show you that as far as the sloshing is concerned, the motion of the liquid in the tank, we can think of it as two different things. So the obvious thing, the one we've just seen, is the wave hitting the side walls of the tank. So that's kind of an obvious thing. And we would refer to that as the global behavior of the liquid in the tank, the mass of liquid as a body moving around inside the tank. So this again is an example. This is in GTT's laboratory. They have what they refer to as a hexapod test rig here, and this is a scale model of a tank. And the hexapod test rig here is moving that tank in the same motion that the vessel might be exposed to in a certain seaway. And then they've got lots of sensors around there, and they're measuring impact force. But also, this is a thing that maybe people are not so aware of, is we also have a local sloshing effect as well. And this is created when, in particular, when you get a progressive wave impacting on a bulkhead. Now, when that happens, and I'm hoping these work. This is such a cool bit of video, I really hope it works.
Do you have it
Yeah.
hold up and start it from
I'm not sure which one it is, but let's take pop-up.
progressive wave?
No, that was the first one. Nope, wasn't that one. Nope, that ain't that one. Okay, I've got another bit of video with little. Okay, if it's not a big disaster, I have something else we can see that on in a moment. Okay. I think on the next slide you can see something very similar to this. Okay. So not quite the same, but virtually the same, particularly if you look at this one here. These are all slow motion shots, and what I'm trying to get across to you here is when a wave impacts onto the side of the bulkhead, it's not just the physical mass of the wave impacting, there is the compression of the gases inside that wave as it impacts. Unfortunately, that last bit of video showed it really clearly, but as that wave compresses the vapor in there as it impacts, that creates a lot of local pressure in addition to the mass of the liquid hitting the side of the tank as well. So again, the point here is to get across that the study of liquid motion in the tank is very, very complex. It's extremely complex. And there's lots of people who've studied this and written books and have done PhDs in the subject. It's a really interesting area, but it's very, very hard to analyze. And there's a lot involved to it. It's not just the massive liquid moving around in the tank. So what causes sloshing? Well, I guess that's pretty obvious, really. We have waves in the environment. We have a vessel that's moving in that environment, and depending on the hull shape of that vessel and the way that vessel's moving through the environment, whether the waves are head-on or on the beam or stern or whatever, will influence the motion of the vessel. And of course, the motion of the vessel in turn will influence the motion of the liquid inside the tank. So it's a very, very complex phenomena, and it's very difficult to analyze. Very difficult. How can we do it? How can we analyze sloshing? Because it's such an important thing. Well, one option is to put instruments on a vessel and make measurements. And in fact, GTT have done that. We have one vessel called the LNG Emo, and she's been fitted with sensors around one of the tanks. But that's not such a great idea, because if you're trying to design something, because it's a bit late, you've built it, so it's helpful in research, but it's not helpful in innovative designs. Another way is to use numerical simulation, mathematical simulation, but this is very difficult. The mathematical simulation of the mass of liquid in the tank is not so difficult. That can be done. But the bit that I was trying to emphasize to you just now, that local behavior of waves breaking, vapor pressures, waves impact onto a bulkhead, much more difficult to do. And it's currently not really feasible to do both of those things together. There isn't the computing power to be able to do that. So at the moment, the best compromise is to use scale models like the hexapod test rig that we saw just now, and GTT will create motions that simulate the motions of a particular vessel in a given seaway, and we can make a lot of measurements from there And from that, we can make estimations of what the sloshing forces are. Now, it's not quite as simple as that because there is a scaling issue. You can't just say this is a 1/25th scale tank and therefore whatever impact forces I measure multiply by 25 and that's the answer. It's not quite as simple as that. But there's a lot of research going on and there's a lot of refinement of these test results that have got it down to the level now where the classification societies take this as the best way at the moment to be able to analyse sloshing forces, impacts and therefore designs.
For this experiment, do you use liquefied natural gas or other fluids?
They use other fluids. Originally, when they first came up with this idea, quite a long time ago, they just used water in the tank. But one of the things that they discovered was it makes a difference depending on the density ratio between the liquid and the vapour that you have above the liquid. And that's particularly relevant, you know, with the waves and the vapour and all that kind of stuff going on. So what they do now is they use a liquid, I don't think I've got it, I don't think I've got it on the slide. I can't tell you from my memory exactly what the liquid is, but they use a liquid with a vapour density above it, which has exactly the same liquid and vapour density relationship or ratio that you would find in LNG and natural gas vapour above it in a tank. So they don't use just water. They use a liquid that has the same density as LNG is the first thing, but the vapour that's above it has the same liquid vapour density ratio as you would find in a real tank. Because it was discovered 10, 15 years ago that makes quite a difference to the impact forces that you record, which is related to the vapours that get kind of compressed, as I tried to show you in those video clips. It's related to those forces as well. Okay, so I know we're going to stop for a coffee in just a moment, but just to sort of finish this up, just to try and explain to you that the way that those model tests are done, the way that we currently analyse the sloshing forces or predict what the forces will be, is there is some software which will determine how a vessel moves in a certain sea condition. So you define the hull characteristics and you define the environmental conditions, the waves and so forth, and this software will give you the motion of the vessel in those conditions. So what we can do from that is we can then take those motions and we can then use those motions in the test rig. So we can use a model test, and we can also use that as an input to some other software where we can use this to analyze the mass of liquid motion, the global motion of the liquid inside the tank. So of course, you can't just do this for one condition. You have to simulate this. They have to do many, many tests. It takes months and months because you have to simulate all the different types of sea condition and tank loading levels that a vessel might experience in its entire lifetime to do a full study, which is exactly what they do. So this type of software will allow us to calculate the drag forces on that tower so we can construct the tower. Then we can then say to the design engineers, here's the forces that this tower's got to withstand. Now make your design capable of withstanding those. And again, as far as the membrane is concerned, we can calculate what the impact pressures will be over the lifetime of the vessel using those. So this is here we go. So this is the calculating the global force, the global motion of the liquid, and so from here we can calculate the drag forces on the pump towers. So that helps us to work out the strength of the pump tower. And here, you've seen it already, this is the hexapod test rig where we can actually measure impact forces on there. And there is, it doesn't actually tell you what the liquid is on it, but there is a particular liquid that they use. But this is the method by which we can take some measurements to help us calculate what the impact forces are going to be. Now, this is a bit of an oversimplification because you don't just measure the impact force, apply a scaling factor and say, that's it, job done. There's quite a complex mathematical process that goes on beyond that to be able to determine what the impact forces over the lifetime of the vessel will be. That's part of what the specialism of GTP is, to be able to do that. So from that, when we've determined what those forces are, we can then design the containment system to be able to withstand those. How can we reduce sloshing? Well, there's three sort of options really. One is to change the design of the tank. So I mentioned to you just now that we don't have LNG carriers with this side-by-side tank arrangement. Well, this was used. Remember I showed you the FLNG, that thing I said was going to be the biggest floating structure ever? Well, this is where their tanks are designed. They have split them in two because it virtually eliminates sloshing as a problem inside there. And also, if you remember, in that floating production unit, all of the production equipment was physically located on the top side here. So imagine the weight, thousands of tons of equipment. So they really needed some central stiffening here on the structure to be able to withstand that weight. So by putting a centerline cofferdam in here as well, it serves a dual function of providing additional physical support for that structure and basically eliminating the sloshing problem at the same time. So our thermal heat flow into that tank is going to be not quite as efficient as if we didn't have that, but it's outweighed by the advantages in this particular. I mentioned about reinforcing the membrane system, so we can reinforce the membrane. There's different ways of reinforcing it. And also, as far as normal LNG carriers are concerned, normal conventional LNG carriers, they have limitations on what levels of liquid they can have in their tank. So when they're fully loaded, so long as the liquid level remains in this kind of green region here, sort of basically above 90% of the tank height, roughly, then that's okay. The impact forces of the liquid shouldn't be a problem. And when the tank is empty, they typically retain a small quantity of liquid in there, which is referred to as heel, to keep it cold. And so long as it's below a certain level, which again, broadly speaking, is approximately equivalent to 10% of the height of the tank. So long as you're within those green ranges, shouldn't be a problem. So what you can't do is sail around at sea with the liquid at these levels, intermediate levels in the tank, because the motion of the liquid could be too much for the structure of the membrane. Which I think brings us pretty much to the end of that little presentation. Okay.
We have a question from the World Maritime University, and they would like a clarification on the pressure inside the tank.
Yep.
In one of the slides, we referred to a pressure of a quarter of a bar.
Yep.
And this appears to be very low value, so they would like some clarification.
Yep. So to clarify that, the IGC code says that the maximum design pressure for membrane tanks, the maximum is 0.7 of a bar, but normally, for most normal membrane tanks, it's a quarter of a bar.
This is above the atmospheric pressure?
Yes, this is gauge pressure.
Okay.
So actually, that's a good point. When I run training courses for the guys on the ships, one of the things we get out of the way right at the beginning on day one is a clarification of absolute and gauge pressure, because that's quite important with LNG. So to be clear, yes, that's a 250 millibar gauge pressure. And so if you read the IGC code, that slide, it said that normally it's 250 millibar, quarter of a bar gauge pressure. But if the scantlings of the inner hull are shown to be strong enough, you can go up to 0.7 of a bar gauge pressure. So again, to clarify, all conventional LNG vessels, membrane LNG vessels that are in operation today, operate with a tank relief valve set point of quarter bar. So it means that the cargo's got to be cold, because outside the scope of what I'm doing here today, but very important to understand the relationship between temperature of the liquid and the saturated vapor pressure of the vapor. Very, very critical. When you come to look at different types of tanks for LNG as a fuel, it's very important to understand that. And again, beyond what I'm here to talk about today, but something that's very important is if you have an LNG bunker vessel that had a Type C tank, where potentially you could go up to about 10 bar pressure, that means the liquid temperature will be much higher at that. And then you try to discharge into, let's say, a ferry that had a membrane fuel tank, you won't be able to do it. Not at that sort of high, 2 bar pressure would mean a high. You can't do it because their tank wouldn't be able to tank it. So this is another consideration. If you have a membrane containment system in your bunker vessel, doesn't matter which type of fuel tank you discharge into, it'll always be okay. But if you have a type C, there's an issue with what you can and can't discharge into. So that's an important factor as well. But that is what the IGC code limits us to. Okay.
Very much. I think that you mentioned this. There is a question from regarding the difference between IGC and the IGF. So you mentioned that they are basically the same, but there are...
Okay, so the IGC code, first of all, is being in force since 1976, I think, and it applies to all vessels that carry liquefied gases in bulk. So that's LPG, LNG, or anything. That's what's covered. So in our kind of field here, where we're thinking about LNG as bunker fuel, it also covers the bunker vessels. Bunker vessels must be built to the standards defined in the IGC code, carrying it in bulk. IGF code is the code that's being under the process of being written and was recently approved, I think in June of this year, at one of the IMO MSC committee meetings. So the IGF code is the code which will specify the construction and equipment of vessels that are going to use low flash point fuels. LNG being one of them. You can have other stuff as well, but
hydrogen.
Yeah, there's other things, but LNG is the thing. So if you're thinking of having a vessel that's going to use it as a fuel, you have to follow the IGF code. Now, in terms of where it's similar, the bit that's definitely similar or probably the same is the bit that defines the tanks. So the structure of the tanks. Actually, it's not exactly the same because the membrane bit is probably the same. The Type C tanks are a little bit different because, one difference I can think of off the top of my head is in the IGC code, only penetrations you can have into the tank are through the tank dome at the top. They're not permitted through the bottom, but the IGF code permits bottom penetrations in Type C tanks because of the way in which we're going to handle the liquid we take off and vaporize it in certain arrangements, depending on the type of gas consumer we have. So there are slight differences there, but to try to be clear about this, the IGC code applies to vessels that carry it in bulk, including bunker vessels. The IGF code will apply to all of the vessels that are using it as a fuel, and it defines all their bunker arrangements and all the other stuff that goes with it.
Thank you very
so
much.
Hopefully that clarifies that.
Let me ask if there are other questions.
Just considering the operation limit, that is one of the biggest barriers to the membrane system and fuel vessel. LNG fuel vessel is a fuel storage. The fuel is consumed, so it is unable to meet the limitations.
But these limitations that I described here are applicable to full-size LNG carriers because of the physical size of the tanks and shape. When we talk about the fuel tank on like a ferry or a container ship, forget it. This is not applicable. Because the size of the tank is so much smaller, then the studies that have been made so far demonstrate that there are no filling level restrictions at all. Because obviously you're correct that if I'm using it as a fuel, I could fill it up today, and of course it's going to go down, and at some point it's going to be in the middle of the tank. So because we're talking a much smaller tank, there are no problems at all in terms of filling limits for a fuel tank on a vessel that's using LNG as a fuel. This is only applicable to big LNG carriers.
Anyways, there is innovation designed for LNG. I guess there will be more investment possible in terms to use the ETL. Have you considered the feasibility study between the types?
I think that kind of study is not something that GTT would look at. That's something for the shipyards and the ship owners to look at, because GTT simply designed tank. And if you were a ship owner and you came to GTT at a pre-design stage and you said, look, I've got this idea, I want to build a tank and like this kind of tank and this kind of vessel for this type of service, GTT will assist you in making some initial analyses and design, and they will check and tell you whether or not it's going to be feasible to do what you want to do. You then, once you've decided what to do, you then go to a shipyard and you tender with shipyards, and they tender for your business, and they will quote you prices and things, and the cost of that is something that they will determine. Once they've done that, they will then come back to GTT and go, right, we're going to actually build this now, and now GTT will produce detailed drawings and design to be able to actually do it. So in terms of the cost, that's really an issue between the shipyards and the ship owners. So it's not something, cost analysis is not directly something that GTT would focus on.
Is there any historical
Well, as I mentioned to you, there are currently 2 LNG bunker vessels that have been ordered and are going to be constructed. There was, at the moment, 1 ferry. This was last year, I think beginning of last year, middle of last year. The project was actually cancelled, but there were designs to build a ferry using a membrane tank as a fuel tank for a ferry, rather than a Type C tank. In the ferry, I think it was 1,300 cubic meters from my memory. So again, when you look at these designs, when you have very small vessels like the ones we have currently, to be honest, it's probably cheaper and simpler to fit a Type C tank. But when you start to look at bigger vessels, like if you look at intermediate size container vessels, for example, that are going to be on longer trades, so they've got longer distances to go between refueling, you're going to need bigger fuel tanks. Now, you could fit more and more. There's a physical limit to how big you can make a Type C tank. But you could fit multiples of those. But as I've mentioned, there are issues then relating to the weight and the space that they're going to occupy. So there comes a point where it would probably be more economical to fit a membrane tank as a fuel tank rather than a Type C tank. So at the moment, the LNG as a fuel industry only has small vessels, and they all use Type C tanks at the moment. We're now starting to get to the point where people are thinking about slightly bigger vessels, and I think now we're going to get a crossover where it's like we could have a membrane or we could have a Type C, and then later on, the vessel size increases and your fuel tank capacity gets bigger and bigger. I think it will be a much easier decision then to say, well, a membrane tank is going to be more logical, because we're going to have so many of these huge Type C tanks. It's going to weigh so much and take up so much space.
Our students are doing individual projects and also group projects where they would probably like to have more details about the sizing, the details in order to, say, install a membrane tank into a design for a bulk carrier or a container ship. So would GTT be interested in some kind of exchange of information in order to...
I might be able to. I know one of the team in France has some presentation slides they've used where they try to explain more or less what I was just trying to say about a crossover point. Exactly how much detail
they can release. Yes.
I don't know. I can find out though.
Okay.
I can find out.
We next year for the individual project, we will send to the West. They can provide us with some. Usually, the designs we have done was for bulk carriers and container ships. We were using Type C, so we would like to see how a membrane will work on such a design. And we have one last question from the World Maritime University. I think it's an easy one. Do you also put membrane at the bottom of the tank?